Welcome to Last Bench Listener. In this session, we are going to discuss about PGP. Yes, we are going to discuss about pretty good privacy technique in email security. Let's first discuss about email security and short introduction about PGP. Following that, we are going to discuss about digital signature and working process of PGP in detail. Let's discuss about email security. In virtually all distributed environments, electronic mail is most heavily used network-based application. But currently email services are roughly like postcards. Anyone who wants could pick it up and have a look at it in transit or sitting in the recipient mailbox. With the explosively growing reliance on electronic mail for every conceivable purpose, there grows a demand for authentication and confidentiality services. We discussed these concepts on previous lecture. What we want is something more akin to standard mails, if not registered mail, which has confidence about the center of the email and its content. That is the classic security services or listed designed. A pretty good privacy secure email program is the remarkable phenomenon has grown explosively and it's now widely used. Largely the effort of the single person, Phil Zimmermann, who selected the best available crypto algorithms to use and integrated them into a single program. PGP provide the confidentiality and authentication services that can be used for electronic mail and file storage applications. It runs on the wide range of systems in both free and commercial versions. Let's consider an example to better understanding of PGP working concept. Just imagine we have a box and we want to put something private in it, something that only those who trust should be able to see, that person as receiver. It's something like a secret email, text message or a picture that make a picture of anything. I will put some flower image here. What would happen if we send that box and somewhere along the way our box gets stolen or opened by attackers? They would probably use it by evil things. So what do? We will use box with lock. Now what happens? In order for the people we trust to see what inside, they need a key. So we send the key in under the box or something like that. If someone steals the box, it will not be long before they find that key and open the box. PGP fixes this. In this analogy, PGP is a box with not one but two locks. Not a one key but two keys. Each key only fits only one of the locks. So key A will fit on lock A, key B will fit in lock B. So each key and lock have different functionality. In our example, key A will be our public key. Public keys are used to lock boxes. Remember, they only used to lock. In our example, key B will be our private key. Private key are used to unlock boxes or messages. Remember, can only be used to unlock. Now, here how we use PGP. If we want to send a message with picture of our flower, we will tell our friend to get the box with two locks and keys, public key and private key. In order for this to work with our friend would have to send with the public key and box. Private key would stay with our friend. This is the most important part of the PGP, keeping the private key safe with the person who wants to eventually open the box. Then put the picture in the box and lock it with the public key. Your friend sent with the box. The next step would be to send your friend the lock box. We said before your friend would be able to open the box because he holds the private key with unlocks the box. And the end your friend able to see your flower pic without worries of anyone else seeing your flower pic. That is very basic explanation of the pretty good privacy. Now we are going to discuss about PGP with the technical terms. Before that we should know about Digital signature. Digital signature is the different from digital certificate. Digital signature is a mathematical technique used to validate the authenticity and integrity of the message, software or digital document. The digital signature equivalent of a handwritten sign or stamped seal but offering far more inherent security. A digital signature is intended to solve the problem of tampering and impersonation in digital communication. Digital signature can provide the added assurance of evidence to origin, identity, and status of the electronic document, transaction, or message, as well as the acknowledging informed consent by the signer. In many countries, including the United States, digital signature have the same legal significance as the more traditional form of the signed documents. How digital signatures work? Digital signatures are based on public key cryptography. Using a public key algorithm such as RSA, which stands for Reversed Shamir Altman, one can generate two keys that are mathematically linked, one private key and another one is public key. To create digital signature, signing software creates a one-way hash of the electronic data to be signed. The private key is then used to encrypt the hash. The encrypted hash is along with other information such as the hashing algorithm, it is the digital signature. The reason for encrypting the hash instead of the entire message or document is that a hash function can convert an arbitrary input into the fixed length of value, which is usually much shorter. This saves time since hashing is much faster than signing. The value of the hash is unique to the hashed data. Any changes in the data, even changing or deleting a single character, results in the different value. This attribute enables the other validate to the integrity of the data by using the signer's public key to decrypt the hash. If the decrypted hash matches a second computed hash of the same data, it proves that the data hasn't changed since it was signed. If the two hashes don't match, the data has either been tampered with in some way, integrity, or the signature was created with the private key that does not correspond to the public key presented by the signer, that is authentication. A digital signature can be used with any kind of messages, whether it is encrypted or not. Simply, so the receiver can be sure of the sender's identity and that the message arrived intact. Digital signature make it difficult for signer to deny having the signed something non-repudiation, assuming that private key has not been compromised. As digital signature is the unique to both document or signer and it binds them together. A digital certificate is an electronic document that contains the digital signature of the certificate issuing authority, binds together a public key with an identity and can be used to verify the public key belongs to a particular person or entity. See this diagram, it explains you to clear view of digital signature. In sender side, she encrypting messages using hash algorithm. Then it generates some hash value. That value will be binds with the sender private key. Then it will create a signed messages. That signed message will send to the receiver with a sender public key. On the receiver's side, when he received messages, then he decrypted the message with him private key, that is receiver private key. Now this digital signature provides the authentication and integrity of that messages. The actual operation of PGP as opposed to the management of keys consists of four services. They are authentication, confidentiality, compression and email compatibility. Now we are going to discuss about authentication operation of PGP. The sequence is listed here. First, the sender create a message. After that, she encrypted a message using such a 1160-bit hash value. After that, they attached the RSA signed hash to the message with using the sender's private key. Receiver decrypts and recover hash code using their private key, and receiver verifies received messages with the hash value. This diagram illustrates the digital signature service provided by PGP. Note this, it assumes the use of RSA digital signature created using the sender's private key and the verified with the sender's public key. Recent PGP versions also support the use of DSS signatures. Signatures can also be detached from a message or file and sent or stored separately. This can be useful to maintain separate signature log of all messages sent or received, or on the executable program to detect subsequent virus infection, or when more than one party must sign a document. Another basic service provided by PGP is confidentiality. It's provided by encrypting messages to be transmitted or be stored locally as files using symmetric encryption algorithm CAST128 IDEA or 3DS in 64-bit feedback mode. The randomly chosen session key used for this send encrypted using the recipient's public RSA key. The steps used in the process are listed. Sender forms the 128-bit random session key. After that, encrypt the message with the session key of the sender, then attaches the session key encrypted with the RSA signature. Receiver decrypts and recover the session key. Session key is used to decrypt the messages. It's providing the confidentiality. This diagram illustrates the both confidentiality and authentication services may be used for the same message. Firstly, a signature is generated for the plain text message and the prependent to it. Then the plain text message plus signature encrypted using CAST 128 or IDEA or 3DES, and the session key is encrypted using the RSA. The sequence is presented to the opposite, encrypting the message and then generating a signature for encrypted message. It is generally more convenient to store the signature with the plain text version of the message. Furthermore, for the purpose of the third-party verification, if the signature is performed first, a third party need not be concerned with the semantic key when verifying a signature. In summary, when both services are used, the sender first signs the message with the own private key, then encrypts the message with the session key, and then encrypts the session key with the recipient public key. Operation is compression. By default, PGP compresses the message after applying a signature but before encryption. This has the benefit of saving space both for the email transmissions and for file storage. The compression algorithm used is zip and is indicated by Z for compression and Z power minus 1 for decompression. Next operation is email compatibility. When PGP is used, at least part of the block to be transmitted is encrypted and thus consists of the stream of the arbitrary 8-bit octets. Next operation is email compatibility. When PGP is used, at least part of the block to be transmitted is encrypted and thus consists of a stream of arbitrary 8-bit octets. However, many electronic mail systems only permit the use of ASCII text. To accommodate this restriction, PGP provides the services of converting the raw 8-bit binary stream to the stream of the principal ASCII characters. It uses radix 64 conversion, in which each group of 3 octets of the binary data is mapped into 4 ASCII characters. Uses radix 64 conversion, in which each group of the 3 octets of the binary data is mapped into 4 ASCII characters. The use of radix 64 expands a message by 33%. Fortunately, the session key and signature portion of the message are relatively compact and the plain text message has been compressed, often by more than enough to compensate for the radix 64 expansion. This format also appends a COC to detect transmission errors. PGP also automatically subdivides a message that is too large for single email into segments that are small enough to send. This diagram illustrates the general operation of PGP and the relationship between the services discussed. On the transmission, if it is required, a signature is generated using hash code of the uncompressed plain text. Then the plain text is plus signature is present is compressed. Next, if confidentiality is required, the black, which is compressed plain text or compressed signature plus plain text, is encrypted and preprinted with the public key encrypted symmetric encryption key. Finally, the entire black is converted to radix 64 format. On reception, the incoming black is first converted back from radix 64 to the binary. Then, if the message is encrypted, the recipient recovers the session key and decrypts the message. The resulting black is decompressed. If the message is signed, then the recipient recovers the transmit hash code and compress it to own calculation of the hash code. PGP makes use of four types of keys. They are one-time session semantic keys, public keys, private keys, and passwords based semantic keys. Each session key is associated with a single message and is used for the purpose of encrypting and decrypting that message. Using the semantic encryption algorithms such as COST128 and IDEO with 128-bit keys, numbers are generated using the ANSI into 12.17 generator with the inputs based on the keystroke input from the user, where both keystroke timing and the actual keys struck are used to generate a randomized stream of the numbers. Since many public or private keys may be in use with PGP, there is a need to be identify which key is actually used to encrypt a session key for any specific message. You could just send a full public key with the every message, but this is insufficient. Rather, PGP uses the key identifier based on the least significant 64 bits of the key, which will very likely be unique. Then, only the much shorter key ID would need to be transmitted with any message. A key ID is also required for the PGP digital signature. Diagram illustrates the format of transmitted PGP message. A message consists of three parts. One is message component and signature, it's an optional one, and finally sessional key component. A message consists of three components. One is message component, second one is signature component, signature should be optional, and third one is session key component. This is also optional. The message component includes the actual data to be stored or transmitted as well as file name and the timestamp that specifies the time of creation, and signature component includes the timestamp encrypted SHA-1 message digest leading to digest actors for the verification and the key ID of the sender public key. Session key component includes the session key and identifier of the recipient public key that was used by the sender to encrypt the session key. The entire block is usually encoded with the radix 64 encoding. Keys and key IDs are critical to the operation of PGP. These keys needed to be stored and organized in a systematic way for efficient and effective use by all parties. PGP uses a pair of data structures, one to store the user's public or private key pairs, their private key ring, and one to the store public keys of other known users, their public key ring. The private keys are kept encrypted using a black cipher with the key derived by hashing passwords with the user enters the whenever the key needs to be used. As in any system based on passwords, the security of this system depends on the security of the password, which should be not easily guessed by easily remembered. This diagram illustrates the general structure of private key ring. When we view this ring as a table in which each row represents one of the public or private key pairs owned by this user, the private key ring can be indexed by the either user ID or key ID. The actual private key itself encrypted using COST128 or IDEA or DDS, keyed using a user supplied passphrase. This diagram illustrates the general structure of public key ring. This data structure is used to store public keys of other users that are known to this user. The public key ring can be indexed by either user ID or key ID. This diagram illustrates how these key rings are used in message transmission to implement the various PGP crypto services, which ignoring the compression and radix 64 conversion for simplicity. The sending PGP entity performs the following steps. First step is signing the message. So first its PGP retrieves the sender private key from the private key ring using user ID as the index. If your user ID was not provided in the command, the first private key on the ring is retrieved. PGP promotes the user to pass the to recover unencrypted private key. Next, the signature component of the message is contributed. Next step is encrypting the message. So PGP generates the session key and encrypts the message. PGP retrieves the recipient public key from the public key ring using her user ID as an index. The session key component of the message is constructed. This diagram illustrates how these key rings are used in the message reception to implement the various PGP crypto services. It's again ignoring compression and radix 64 conversion for simplicity. The receiving PGP entity performing the following step. First step is decrypting the message. So PGP retrieves the receiver private key from the private key ring using the key ID field in the session key component of the message as an index. PGP promote the user for the passpass to recover the unencrypted private key. PGP then recovers the session key and decrypts the message. Next step, authenticating the message. PGP retrieves the sender public key from the public key ring using key ID field in the signature key component of the message as an index. PGP recovers the transmitted message digest. PGP computes the message digest for received message and compresses it into the transmitted message digest to authenticate. The PGP documentation notes that this whole business of protecting public keys from the tampering is a single most difficult problem in practical public key applications. Its solution is to support a variety of formal and informal environments in which any user can act as a CA to certify another user's public key and then act as trusted introducer to other users, thus forming a web of trust. PGP provides the convenient means of using trust, associating trust with public keys and exploiting trust information. The key ring is regularly processed to derive trust indicators for keys in it. Associated with each such entry key is a key field that indicates the extent to which PGP will trust that this is a valid public key for this user. The higher level of the trust, the stronger is the binding of the user ID to this key. PGP allows the user to revoke their current public key either because compromise is suspected or simply to avoid the use of the same key for the expanded period. In this session, we discussed about email security, PGP introduction, actual operation of the PGP. They are authentication, confidentiality, compression, and email compatibility. After that, we discussed about 4 types of keys: one-time session semantic key, public keys, private keys, and passpass based semantic keys. Finally, we discussed key rings and key management. I hope you understand this session. In next session, we are going to discuss about secure and multi-purpose internet mail extension in detail. Thank you for watching.